Now, we will talk about the connected graph. A graph is said to be connected if there is a path. If there is a path from any vertex to any other vertex, in the sense every two vertices are path connected, in the sense every pair of vertices are path connected. Otherwise, we say the graph is disconnected. We can see an example. This is connected. V1, V2, V3, V4, V5, V6. You can come from, you can reach from any vertex to any other vertex. So this is connected. One more example is connected. You can come from here to here, here to here, here to here. So it's V1, V2, V3, V4. You may feel that V1 and V4 are not connected, but they are connected through V2, V3. So they are connected graphs. This is a closed connected graph. This is an open connected graph. Disconnected graph is, look at this. V1, V2, V3, V4. This is U1, U2, U3, U4. Now you have 8 vertices. These two are disconnected because there is no path from V2 to U1. Look at this. This is U1. This is V2. You cannot travel from V2 to U1 through any path. There is no path, in fact. K connected. A graph is said to be K connected that means I must have K vertices. K connected if at least K vertices must be removed at least K vertices must be removed so that to render the graph G disconnected. That means you see a graph, it's K connected means if you remove at least K vertices, then the remaining graph should be disconnected. That's called K connected graph. That means it is connected by at least K elements. A graph is said to be acyclic. A graph G is acyclic if it has no cycles. Already I have defined about the cycle. Cycle is a path starting from V1 to V1, reaching to V1, V1 to V1. A very important concept is, let G be a graph. H be a subgraph of G. Look at the definition. We have a graph, we have a subgraph. H is said to be component. H is said to be component if there is no larger subgraph H dash such that H is strictly contained in H dash. Means the vertices of V is contained in vertices of V dash, edges of H is contained in H dash is not possible. No larger subgroup. There is no larger subgroup bigger than H contained in H dash. Then this is called the component. Also, H is called, also in this case, H is called the maximal, is called a maximal. H is called a maximal subgraph of G. That means because there is no other subgraph bigger than H. So H is maximal among the subgraphs. I'll make a note about this. Intuitively, G can be partitioned into disjoint components. That's what we have to see. H is. Let us see an example. Look at this. This is V1, V2, V3. V1 to V3 there is a path. I have an edge from V4, V1 to V4, V4 to V3. This is an edge. So I can say E1, E2, E3, and then V5, V6. This is a graph. Let us see the components. So there are 3 components in this graph. In this graph there are 3 components. What are they? Let me write down the component C1. Don't get confused. Already I have written the symbol Cn is a cyclic graph on n elements. So component C1 is, we will see V1, V4, V3. If you write V1, V4, V3, that's a component. That is a subgraph. What are the edges of this? This is V1. Let me write down E1, the subgraph of H1. What are the edges? The edges are E1, E2, E3. So this together, the vertex set and as well as the edge set, that's a subgraph. It is a component. What are the other components? The component C2. singleton V2 only, there is no edge. It's a component, subgraph. What about C3? C3 is V5, V6. The edge I can write down as E4. So this is vertex set, this is vertex set. I'll say V2, this is V3. The edge set E2 is empty. What about this? V5, V6, E3. What is E3? Only E4. So this is a component, this is a component, this is a component. So there are three components. Hence, component means a maximal subgraph. This is H1 is a subgraph. There is no other subgraph bigger than H1. You can see. You can easily see there is no subgraph bigger than H1. Suppose if you want to add one more vertex, if you add V2, there is no edge. So it cannot be a subgraph. What about V2? If you add one more, say for example either V1 or V3 or V4 or V5, there is no edge connecting them. So this is a maximal subgraph, which is a component. Also, look at this example. V1, V2, V3, V4, V5, V6. That's a graph. Now, I just leave for you to, I just leave this for you to write the components. How many components are there? How many components are there? What are they? For example, can I write V1? I'm just writing V1, V4, V1, V5. Will it be a component? Is there any other component bigger than this? So just try whether this is a component or not. Now, an important theorem definition is digraph. Digraph is a graph G is equal to VE, where E is an ordered pair of vertices. Ordered pair means in the sense that every edge has an orientation. Orientation means direction. So now let us see a digraph. A digraph means a graph with a direction. V1, V2, V3, V4. That's all. This is a digraph. Now, how do you represent this digraph? Namely, V is simply V1, V2, V3, V4. This is what you know. What about edge set? Now, you should be careful. Edge set is, there is no V1, V2. So, you will have V2, V1. Now, you have to be careful about writing V2, V1. Then, V3, V2. Then, V4, V3. V4, V1. V2, V1, already I have written. I must get 5 edges. So, V4, V2. Now, there is a meaning. V2, V4 is not there. Clearly, V2, V4 is not an edge in this graph. I mean, we have many of this kind. Every edge should have an orientation. It is an example. Example 1, example 2. Now, what is a pseudograph? A pseudograph is a graph in which I mean, a pseudograph is a graph in which multiple direction of edges are allowed. Edges of same orientation between two vertices are allowed. What does it mean? Let us see the same graph. Now it is a digraph. I'll write down like this. Again, another edge. So I'm allowing multiple edges. Edges of same orientation between two vertices are allowed. How many edges? Many edges. Edges more than one. Edges more than one. Edges, I'm writing here again, more than one. Of same orientation between two vertices are allowed. This is an example. I can write down another example. This is a pseudograph. That's all. See the difference between multigraph and pseudograph. Multigraph, there are edges, no doubt, but the direction is not given, because in multigraph there is no direction. It is simply a graph. Whereas I am talking about the pseudograph in which edges of the same orientation are allowed. Now we will talk about, let G be a graph and U comma V belongs to V of G, a vertex set of G. The distance between U and V, the distance between U and V denoted by DUV is defined as the smallest defined by DUV is defined as the smallest length between, or length or the smallest path, actually the smallest length between U and V. That's DUV. Now, the diameter of a graph, the diameter of a graph G denoted by dia G is defined as dia G is the maximum length between the vertices, between any two vertices. So Write down all the vertices, lengths of all vertices, pick up the maximum. Then it's called the, let us look into an example. V1, V2, V3, V4. This is V4, V5, V6, V7, and there is, let us calculate the radius and diameter. For example, distance and the diameter. So I want to calculate distance from V2 to V6. V2 to V6, how do you calculate? See, from V2 I can reach V7, V4, V7, V6. If it is from V1, it is same. V1, V4, V7, V6. So let us see, from V2 the shortest path for me is to reach V4 by one step. V2 to V4. Then V4 to either V5 or V7. Once if I reach V7, I have to reach V6. So 1, 2 and 3. Which is 3. What is diameter of G? Diameter, obviously you have to check from V2 to V6. So from V2 to V6, if you want to check, what is the path? 1, 2 and 3. 1, 2, 3, 4. So now what you have to, maximum length between any two vertices, of course it should be shortest path from DV6. So 1, 2 or 1, 2, 3. So that diagram of. What about the diameter of V3, V6? Sorry, distance of V3, V6. V3, V6 is 1, 2 and 3 again. What about diameter of V4, V6? It's 2. V4 to V5, V5 to V6, or V4 to V7, V7 to V6. Let us see another example. V1, V2, V3, let me write down V1, V2, V3, V4, V5, V6, V7. Now, the same technique for diameter of what is V2, V7. V7 and V6 are the same distance to V2. So, D of V2, V7. 1, 2, 3, 4. Is there any shortest? No. What is the diameter of the G, the graph? Diameter of the graph is, again, You have to check either V2 to V6 or V2 to V7. V2 to V6 or V2 to V7, that is the farthest. So V2 to V3, V3 to V4, 1, 2, 3, 4 or 4. In both the cases, diameter of J is 4. Now, look at this. Maximal length between any two vertices means, what is the, if you count like this, it is false. 1, 2, 3, 4, 5 and 6. See, 1, 2, 3, 4 and 5. Because once you reach V5, immediate step is V7. If you want to reach V7, immediate step from V5 is V7. So you cannot travel to V6 and then you cannot come to V7. I would like to talk about the cut vertex and bridge. Before that, let me give a small cut vertex and bridge. Before that, let me define another concept. Let G be a graph. And V is a vertex. V belongs to V. If I write V, V is a vertex set. Then G minus V is a graph, in fact subgraph. In fact, it is a subgraph obtained from G by deleting all its edges incident to V and V and the vertex V. You have to delete both. Let G be a graph, V belongs to V, then G minus V is a graph obtained from G by deleting all edges incident to V and then hence V is called a cut vertex. Cut vertex or cut point. The same way of defining an edge, let G be a graph, then G minus E is a graph obtained from G by deleting the only edge E. See the difference between cut vertex and bridge. Actually, bridge is nothing but cut edge. Cut edge means you cut the edge, which is a bridge. Cut vertex means the vertex which has to be removed. See, G minus V is a graph obtained from G by deleting all its edges incident to V and as well as the vertex. You have to remove the vertex and which are all incident to this. I want to see the same for this. For these two, the same example, I will call this as A, B. In example A, let us see what is a vertex. Look at this V4. V4 means look at this, V4, I am removing V4. So V4 is a cut vertex. Why? I want to remove all the, so I have to write down everything. Look at this. I will write down V1, V2, V3. These edges are same because there is no change. What about V4? V4 I have to remove. If I want to remove V4, I have to remove the edge incident to V1, incident to V2, incident to V3. But V1, V3 is no problem. So I have removed V4. I have to remove even V4 also. So if I remove V4, this edge also has to be removed, this edge also has to be removed. So I will get this. V5, V6, V7. So if you remove this, V1 to, this is a partitioned graph, V4 is removed, so V4 is a cut vertex. V4 is a cut vertex. And no bridge. There is no bridge. Why? Suppose if I want to remove this one, still I can travel from U2 to U3. Any of the, you remove any of the edge, we can reach to anywhere, from any vertex to any vertex. So V4 is a cut vertex, whereas it has no bridge. In example B, what is V4, V5? This is, usually we write V4, V5, which is the edge. If you remove this, edge means you have to remove edge. So V1, V2, V3, V4, vertex will be there. You have to remove only edge. So you'll get V5, V6, V7, V5, V6, V7. So now I want to just modify this in a different way. Let G be a connected graph. And V belongs to V. G minus V is a graph obtained from G such that G minus V is a disconnected graph. Hence, V is called, in this case, V is called a cut vertex. The same I can use, let G be a connected graph, E belongs to V, let E belongs to E. If G minus E is disconnected, is obtained from G such that G minus E is disconnected, in this case, then E is called an edge. Sorry, E is called a bridge. Finally, I would like to, you can find out some of the graphs like this. Find out cut vertices and edges or bridge. You have some more like this. You can see this. Finally, I want to wind up this session by looking at the definition of in degree and out degree. Definition of in degree, out degree of a vertex V. So if I want to do this, the definition is, let G be a digraph. I'll define in degree and out degree in a digraph. Already I have defined the degree in a graph. Let G be a digraph and V belongs to V. In degree, in dV, the in degree of V. Similarly, out degree of V denoted by in degree V, out dV is defined as the number of edges incident towards V. Out degree is the number of edges incident outwards, towards and outwards. This is inwards. I'll write down the in degree is defined as the number of edges incident towards V. Number of edges incident outwards to V. Now we'll finally look into this. An example. V1, V2, V3, V4, these are the arrows. Now let us calculate the in degree, out degree. In degree plus out degree is degree. Let us see V1. How many edges are incident towards V1? There is only one from V4. So in degree is V1. What about the out degree? Out degree means away from V1, which is 1. So the total is 2. So the degree of V1 is 2, 1 plus 1. What about V2? How many edges are inside or towards V2? There are 2, namely this and this. How many are outward? 1. So the total is 3. What about V3? V3 has 1 in degree, 1 out degree. What about V4? V4 has 2 in, 1 out. So 3. Look at the total, 10. The same old handshake lemma. handshake lemma speaks, the the sum plus dv3 plus dv4 is equal to, the dv1 is 2 plus 2 plus 2, which is 10, which is equal to twice the number of how many edges are there? 1, 2, 3, 4, 5. There are 5. So in a digraph, we can talk about the integrand, outegrand. So these are all the basic notions for the graph theory. We have done a lot of things like graph, multigraph, simple graph, subgraph, isomorphic graph, complete graph, bipartite graph, complete bipartite graph, regular graph, many of cyclic graph, graphs with cycles, and acyclic graphs, many things we have, connected graphs, many things we have done.